Okay, let's recall that in the last analysis video, the video ended with this statement, that is this lemma, where we see the elementary properties of closure subsets. So today let us start the video by proving this. Actually, in the text only a part of the proof is there and the rest is left to the exercises, but we are going to prove it fully here itself. So the statement is just this: x and y are any two subsets of R, any two arbitrary subsets, then these things happen. And among them, the first one is this: x is contained in its closure. In other words, every element of x is an adherent point of x. So let us prove this first. So we choose an arbitrary element of x. Now to prove that small x is an adherent point of x, what do we have to show? We have to show that for any positive real number epsilon, there is an element in this set x that is epsilon close to small x. Now since small x itself is coming from x, that element can be chosen as small x. So it's actually something really trivial. Then for any positive real number epsilon, there exists x in x such that x is epsilon close to x because the distance of x from itself is 0. This implies x is an adherent point of x, or the same thing, that x belongs to the closure of x. Hence, x is a subset of its own closure. Okay, so that is the first claim. And then we have some other things involving union and intersection of sets and their closures. But before we get to these things, let us prove this one instead, which can be used to prove these things in a somewhat quicker manner. Okay. So now we want to prove that if x is a subset of y, then the closure of x is a subset of the closure of y. Next, let x be a subset of y. So now we have to prove this containment. So let us take an arbitrary element in this set, this closure. Let y be any element in x bar in the closure of x. Then then that just means that y is an adherent point of x. But you need not keep on writing this every time. Okay, it's known. That's what it means. Y being in this set is equivalent to y being an adherent point of x. So we can directly write, then for any epsilon greater than 0, there exists some element y prime in x that is epsilon close to y. In other words, the distance between y and y prime does not exceed epsilon. But okay, now you invoke this condition that x is contained in y. So y prime being in x must also be in y, in the set y. But since x is a subset of y, y prime belongs to y. So now what are you having? You are now having an element y prime in y, that is epsilon close to y. And it does not matter what epsilon is. For that epsilon, you are going to get one y prime in x. Of course, if you change epsilon, the y prime will change. But because x is a subset of y, every time you have one such element, it's going to be in y after all. So that is why your original element, that is y, now becomes an adherent point of capital Y. Thus, y is an, if you want you can directly write thus y belongs to the closure of capital Y, but let me just write this for once. i.e. y belongs to y bar. So any element in x bar is also in y bar. So the closure of x is contained in the closure of y. Okay, so we have proved that thing. And now we go to those other properties involving unions and intersections. And let's do that in another paragraph. Since you have these containments, x intersection y is a subset of x, and that is a subset of x union y, and at the same time x intersection y is a subset of y, which in turn is a subset of x union y. It follows from the above paragraph. Okay, now we can just simply put closures on these sets, and still we will have containments. Okay, that follows from what we have proved just now in the above paragraph. So that's why I wanted to prove this thing first. This property by itself will not give us everything. We will have to do something else also, but it gives us a significant portion of that, of these two other properties which involve union and intersection. Okay, so from the above paragraph, that the closure of the intersection is contained in the closure of x, and that is contained in the closure of the union, and just like that, the closure of x intersection y is contained in the closure of y, which is contained in the closure of the union of x and y. Now from these containments, we are further going to get these next things. So, Okay, so let us first see the intersection, this set, the closure of the intersection. It is a set that is contained in this set as well as this set. So it will be contained in their intersection naturally. So the closure of X intersection Y is contained in the intersection of the closures. And if you go back to the statement, you will see that this is in fact one of the things that we needed to prove. So this in fact we are just getting directly, okay, as a consequence of all these things. And we also get something else from these other containments. X bar and Y bar are both contained in this set, so their union is also contained in that set. That is X bar union Y bar. It's a little cumbersome to keep calling closure, okay, and these things. So let me just simply call these things X bar and Y bar. But that other property involving union does not ask us to show just simply this. It demands equality. So that means we have to now prove the reverse inclusion also. That is, this also should be shown to be contained in this. And that we have to do. Okay. So for that, we take any element in this. Now our aim is to show that this Z or Z belongs to the union of the closures. Suppose that is not the case. So that means we will try to arrive at a contradiction. Suppose this does not belong to this union. Now an element not being in the union of two sets means that it belongs to neither of them. Because if it belongs to at least one of them, then it belongs to the union. Then this does not belong to X bar and this does not belong to Y bar. Now being in closure means what? Being in closure just simply means that for every epsilon something happens. Okay, that condition. Not being in closure is its negation. That means for no epsilon that thing, not just that. What I am trying to say is this, I messed up. Z not being in the closure of X means Z is not an adherent point of X. That means that whatever we have, that condition that you have in the definition of an adherent point is not true for Z. So for Z, every epsilon will not work, will not give you that condition. So there is at least one epsilon for which that condition is not true. That is, there exists, actually for this one also we will get another epsilon, so let's name them epsilon 1 and epsilon 2 such that you will not find any element in X that is epsilon 1 close to Z, and at the same time you will not find any element in Y, in the set Y, that is epsilon 2 close to Z, and that is equivalent to having this thing. this is empty, and this is empty. Why? Why though? You see, this open interval in R represents what actually? If you just think about it, it is by definition the set of all real numbers z prime or z prime such that these inequalities are true, right? But these inequalities are equivalent to these inequalities if you subtract z from all the terms here, and these inequalities in turn are equivalent to this one. Right? Okay, so that means z prime is epsilon 1 close to z. So that's why z not being in x bar means we won't find any z prime in x that is epsilon 1 close to z, and that is equivalent to this interval being disjoint with x, because otherwise in that intersection you will find one such z prime. Okay, so that's why you are having these disjoint intervals with x and y respectively. Let me just keep it like this. Okay, it's not a part of the proof, but then I think things will look simpler if we assume that one of these is smaller than the other. We can assume without loss of generality. Without loss of generality that epsilon 2 is less than or equal to epsilon 1, then clearly this interval will be a subset of this interval. Not going into the details of why that happens, you understand how this containment follows from this inequality. And because of this, this is disjoint with x union y. Do you see how? Let us see in detail. Suppose you try to calculate this intersection using the fact that set theoretic identity is there. No? Intersection distributes itself over union. Say we want to calculate this intersection. then by that distributive law from set theory, this is equal to this intersection X union this interval intersection Y. Okay. Fine. Now note that this interval is contained in this interval, and this interval has no point in common with X. So the smaller subset also cannot possibly have anything common with X. So that's why this first intersection is empty, and this of course is empty, that we see here directly. So that's how we are getting this thing. Now what does this final equation tell us? It tells us that no point of X union Y is epsilon too close to Z, right? Because there is no common element, and we know that if a real number has to be epsilon too close to Z, then it has to belong to this interval. But that's not the case that we can see here. So we can write like this: thus no element of X union Y is epsilon too close to Z. So Z is not an adherent point of X union Y. But this is a contradiction, because Z has been chosen to be an element, a point in the closure of X union Y. So it has to be an adherent point. So this contradicts this our starting point, that Z in fact is coming from the closure of X union Y. So that means our supposition, the last supposition, has been erroneous. It is wrong. So our last supposition is wrong, i.e., so what was the supposition? Namely, we supposed that Z is not in the union of X closure and Y closure. So that cannot be the case. So it has to belong to the union of X closure and Y closure. Thus, but Z was an arbitrary point of X union Y closure. So this is also contained in this. But the other inclusion, the reverse one, we have already proved that. Hence, now we can finally write equality. So if we have union, we get equality. But in case of intersection, we just simply get containment. There are examples which show that we cannot have equality in general when we have intersection. Okay, we will see that. But let us now next see our next result. These are a few things that we need in our study of continuous functions, which are topological in nature. We will see topology in general. A little study is there in this text itself. We will see when the time comes. But let us now next see what the closures of intervals are in this next lemma. Intervals seem to be quite important for us in real analysis, so it is natural to ask what closures of intervals are. Closures of intervals. Let A and B be real numbers satisfying this inequality. And let I be any of the four intervals that you can think of that has A and B as its endpoints. Yeah, any one of the four intervals, open and the two half open, and the closed, then the closure of I is the closed interval. Yeah, instead of writing in words, let me just use the symbol, the notation. If I is any one of these four intervals, then its closure is this one, the closed one. Similarly, yeah, the rays. The closure of this closed ray is equal to the closure of this open ray, that is equal to the closed ray. And if minus infinity is one of the endpoints, then the closure of this closed ray is equal to the closure of this open ray is equal to this closed ray. And it's not over yet, there is something else also. One exercise has been devoted to the proof of this lemma, but we won't do it in the exercises. Okay, for this one also we will prove it here itself. However, I won't fully prove the whole thing. I won't prove the whole thing here. I will just maybe I will prove, say I will take I to be one of these things, and then I will show that its closure is this, and from here I will choose one of the sets and I will leave the rest to you. And in the exercises also I won't do it. Okay, it will be left to you. Finally, the closure of this entire real line is this itself. Looking at these things, you may be tempted to write closed interval here. That will be the extended real number, the set of all extended real numbers. But that would be wrong. Okay, do you see how? Why? That's because you see the closure of a set, suppose you have x, right? X is a subset of R. What is the closure of X by definition? By definition, it is the set of all adherent points of X. And by definition, an adherent point of the set X is a point which satisfies some conditions, but it's a point from where? It's a real number first and foremost, and then it satisfies some conditions. It loosely speaking, it sticks close to X. Okay, so that's why it adheres to X, so it's an adherent point. Now, minus infinity and infinity are not real numbers, so they are not covered in this definition of adherent points, so they cannot belong to any closure. Okay, not yet. They can be made to belong, but those things will come later. What I am saying here is that for any subset X of R, the closure of X by its very definition is actually again a subset of R. So there is no question of this closure being this closed interval. No question of including minus infinity and infinity in the closure, because they are not real numbers. Okay, so let us start the proof, but I think I need a little ink first. Instead of a rigorous proof, I will give a sort of hint only, elaborate hint, and I will ask you to write the rigorous proof yourself. Because if you just keep seeing these things and don't go through the struggle of trying to write a rigorous proof yourself, then you will never learn this. So which one should I choose? Let me choose this one, okay, as my capital I proof. Let capital I be this half open interval. Actually, I could have chosen this one. In fact, this one is the, I won't say the most difficult, but anyway, let's just do this itself. All right. Now, we are immediately going to use the properties of closures that we have seen in the previous lemma. Then, I itself is contained in I closure. So that means we know that whatever I closure ultimately is going to be, I mean the claim is of course this, it has to contain I in it. Alright. So that means this interval itself is a part of the closure. So what else are we missing? In this interval we have all the real numbers lying strictly between A and B. Okay. So we get those things here. And in this interval we also have B. B is an element in this interval. So we are getting B. But the extra A we are not getting from I. So now you have to prove that A is an adherent point of I, and hence A also will belong to the closure of I. And now we try to show that. And in showing that, let me just draw a figure. And this you should always do whenever you are trying to think of such things. think in terms of a figure. It's not very difficult. When you are doing analysis in higher dimensional space, it will become somewhat difficult to think of what is going on in terms of a figure. But here it's quite clear, there is only one line. Right, so here somewhere you have A, and to the right of A, somewhere you have B. Okay. So now the situation is this. You have to show that A is an adherent point of this interval. And what does that mean? It means that if you are given any epsilon greater than 0, then you should be able to find an element in this interval that is epsilon close to A. Okay. Now the epsilon can of course be anything, large or small, any real number, but positive. Suppose epsilon is quite large, so large that I can't possibly show that here, but let me just try. Epsilon is so large that A plus epsilon, say A plus epsilon is this point. That A plus epsilon exceeds B. That can happen because no one is restricting you to choose epsilon to be small. We normally say epsilon is small, but in mathematics there is no absolute meaning of these words, small, large. These are vague words, right? On this side also, somewhere means at an equal distance from A, on the other side, you have A minus epsilon. So now, in order to have a point from the interval that will be epsilon close to A, you just have to choose a real number that is within this interval itself. But that is really easy, because the set from which you have to choose that point itself has been included in the interval itself. So you can choose whatever you like from here. In particular, for example, you can choose B itself. B epsilon is so large that B itself is epsilon close to A, because the distance between A and B is this much, that is less than epsilon. But your epsilon can be small also, it may not be large. So that A plus epsilon lies to the left of B. That is the other situation. Let me just draw another one for that situation. So this is A, this is B, and say your epsilon now is somewhat small, so that this is A plus epsilon and this is A minus epsilon. Again, your job is to find at least one element in this interval that is epsilon close to A. So naturally you will have to choose it in such a way that it also lies in this interval, but at the same time you are choosing from this interval. So that means it should lie in this region. Now, will you always have points in this region? Yes, you will have. Why? Because, for example, you can choose, you of course have infinitely many points in this interval, but one particularly easy one among them is the middle point. Middle point of what? Of these two boundary points of this interval, and that is nothing but the arithmetic mean, simple average of those two boundary points. That will lie in the middle, and that belongs to, that is coming from the interval I, but at the same time that is, since it belongs to this interval, so it is epsilon close to A. Its distance from A is less than epsilon. Okay, so you can see that here, instead of choosing B, in order to bring uniformity, okay, to the situation, instead of choosing B, you could have chosen here also the middle point of A and B, that is your simple average A plus B over 2. So what do you see here that we are doing that is the same in both these situations? Namely, we see that which one of these two numbers is closer to A. Here B is closer to A than A plus epsilon. In this second case, A plus epsilon is closer to A than B. That number we choose and we consider the arithmetic mean of that number and A, and that gives us a point in our interval that is epsilon close to A. So that gets the job done, right? So this is something that of course is not a part of your proof, but you should think about it, maybe as a rough work. And all these things now we are going to write systematically, but also at the same time somewhat briefly. This is the heart of real analysis. Whenever you think about something in analysis, at least in one dimension, that is ordinarily what we know as calculus, you should always think of some such figure, a part of the real line where you put the points or think of them in some way, and then things will actually become quite natural. So I don't see why people find analysis very difficult. It is very natural. In fact, algebra is quite difficult, and so is topology. Okay, so we are now going to write like this. What should we write? Now the next thing we are going to show is that A is an adherent point of I. So we have to choose epsilon, of course, first. But let us mention next, we show that A belongs to the closure of I. Choose epsilon greater than 0. Then should I use the notation of minimum of, let me just use that. Instead of calling that also something else, let me just do it directly. Then A plus minimum of A plus epsilon and B over 2. You understand what that mean is. That mean is, in this case, in this first case, that mean is B, and in this case that mean is A plus epsilon. It's going to be one of them. This belongs to I such that its distance from A is less than or equal to, actually it will be less than epsilon, but we do not need strict inequality this. Thus A belongs to I. So already we have this much in I closure, but now additionally we also have A. So the closed interval itself is a subset of I closure, but that by itself does not say that it should be equal to I closure. There may be something else also, outside, but we have to prove that no point outside of this interval itself except A is an adherent point, and for that there is another figure. And let me just make a remark at this point. Having seen these things, it is now clear to us that this will happen. But you have to remember, it's this part, this sentence, then this, such that this also has to be proved, actually proved. Okay. How is it that this real number belongs to I? You have to show this, and showing that thing is left to you. Similarly, you also have to show that this inequality is indeed true. Okay, that is also left to you. But now let's see the other thing, that no point outside of this closed interval can be an adherent point of I. So by now you have understood, I think, clearly that any such thing, whatever we write, involves such a figure in the background. So now our focus is this closed interval a comma b. We know that it is a subset of the closure of I. But what about points outside of it? Points outside of this closed interval can either lie to the left of the interval or to the right. Let us consider a point here to the right. Say we call it C. Our aim now is to show that C is not an adherent point of I. Oh, by the way, keep in mind, our I is the open closed interval, not the closed interval itself. So in order to show that C is not an adherent point, you should choose a region around C small enough so that within that region you cannot choose any point from I. In other words, that region is disjoint with I. And if this region means open interval, of course, has length 2 epsilon. That means epsilon on that side, epsilon on this side. So the interval actually is C minus epsilon, C plus epsilon. Then you won't be able to find any point from I that is epsilon close to C, because in order to be epsilon close to C, that point has to be here. But that is not possible because of this disjointness. So that means in trying to show that C is not an adherent point of our I, you should choose epsilon small enough. But how small? That you can see from this figure itself. There are infinitely many choices for epsilon, but to be specific, we can choose epsilon to be the midpoint of B and C. So you also see that considering midpoints is quite easy. If you choose your epsilon in such a way, well, epsilon itself is not the midpoint, but the midpoint should be C minus epsilon. What does that need? What do we have to do in order to get that? So this part is also rough work. So it's still going. We need C minus epsilon to be the midpoint of B and C. So from this we can calculate epsilon. This implies C minus B plus C over 2 is equal to epsilon, or epsilon is equal to 2C minus C will be C minus B over 2. So our epsilon should be C minus B over 2. But also we should have epsilon positive. Will it be positive? Yes, it will be positive, because C is greater than B, and that's why C minus B is positive, so half of that is also positive. By the way, why is C strictly greater than B and not possibly equal to B? That's because our interval I has B in it, and B already is in B is in this closed interval, but we are now trying to see that points outside the closed interval are not adherent points. So C is strictly greater than B. So in the solution, of course, you will start like this. Let C be a real number that does not belong to this closed interval. Suppose C is greater than B. Then for epsilon equal to C minus B over 2 greater than 0, the open interval centered at C and having length 2 epsilon is disjoint with I. Thus, C is not an adherent point of I, i.e. C does not belong to the closure of I. And there is another half. If your C lies here, then also you have to do something similar. Well, here the role of B will be played by A, but be careful. B belongs to your original I, but A does not belong to your original I. So some slight difference may be there. Okay, so this part you have to do. Once you do that, then you have shown that fine, this is a subset of I closure, but nothing else is in I closure. So that means it has to be equal to I closure. And then you can finally write, after doing all those things, you can finally write that I closure is equal to the closed interval A comma B. You may have seen in many places in analytic arguments things that start like this, and you may wonder where these things come from. So they come from such back calculations and geometric considerations. Okay. Now, if I choose say one of the rays, let me just simply arbitrarily choose this. Okay, which extends without any bound to the left of A, but it stops at A. Or you may think of it as starting at A and going on that side. Again, we know that the set itself will be contained in its closure. Alright, so that means we are in fact getting whatever we want in the closure from the set itself. Because what is the claim? The claim here is that this is equal to this. So that means all now you have to prove is that no point outside of this interval is an adherent point of this interval or this ray. Again, same thing. You have A here. You choose an arbitrary point C, same procedure. And in this case, what is even better is that there is no other case where C lies to the left of A, because the left of A is entirely contained, it is I. Okay. So if you have to choose a point outside of I, it should lie to the right of A. So here also, no matter what C is, no matter how close C is to A, you have to choose an epsilon small enough such that this open interval is disjoint with the given ray. That's it. This will show that you cannot choose any point from the ray that will lie within a distance epsilon from C. So C cannot be an adherent point. So points outside of this ray are not adherent points, and that is why you will get equality. And similarly, you can also show this. In fact, in this case, there is really nothing to show. Once you start thinking about this, you will realize why I said so. Okay, so that is the rather sketchy and incomplete proof of this result, but the other parts you have to do yourself. Now, before I end this video, let me just see another lemma, the next one. We do not only have intervals in R, we have other sets also that are important. Their closures can also be calculated. So the next lemma is about that. 13. The closure of, instead of writing so much, we can just simply write like this. We have the closure of the set of natural numbers is the set itself. The closure of the set of integers is also the set itself. But the closure of the set of rational numbers is the entire set of real numbers. Then the closure of the set of real numbers is itself, and the closure of the empty set is the empty set. Now, instead of actually giving the proof itself, let me just show the things geometrically so that you get the basic idea. So that's why it's proof star. So if you think of the set of natural numbers, now let me show it on that side. Always think about these things geometrically as far as possible. Sometimes of course your geometric intuition will not give you the exact thing, but still figures are always helpful. So let me draw the number line like this. Here you have 0, 1, 2 and so on, and on this side you have the negative integers, and they also go on without any end. So our n is only this part, right? It starts from 0 and goes like that. So what we are saying is that the closure of n is n itself. N of course is contained in its own closure. So you just have to prove that nothing else is in the closure. Nothing else means, whatever else you have in the set of real numbers either then lies to the right of 0 or to the left of 0. If it lies to the right of 0, but it's not in n, right? So it will be some fraction. It will not be a natural number. So it may lie either here or between 1 and 2 or between something and something. Now among those somethings, you will always find like this. Say your x that you are choosing in R which is not in N, suppose your x is greater than 0, then you will always find a natural number N that will satisfy this. But why? From where are we getting this fact? For that, you recall exercise. We have already solved this long ago, exercise 543. Back when we were developing the system of real numbers, there we proved this. And in fact, this exercise gave rise to the greatest integer function. Actually, you have the possibility of equality here, but because x is not in N, so we are going to have strict inequality. In fact, if you use the notation for the greatest integer function of x, then this inequality can also be written like this. But whatever the case is, just for the sake of simplicity, suppose our x lies here. Now, in order to show that x is not an adherent point of N, what do you have to do? Again, you have to find a region surrounding x, including x in it so small that no point of N lies in that region, and that you can see is it's quite easy to see geometrically. Okay, but if you really want to know in this case what the epsilon should be, then you have to consider the distance of this left boundary point from 1 and the distance of this right boundary point from 2. You will have some distances. Among those distances, the minimum one you should choose as, well, I should not say as epsilon, but the minimum one will give you the epsilon. But the details I leave to you. If you do not get exactly how to write these things, let me know in the comment section. But if your x lies to the left, fine. There also, okay, so lying, if x now lies to the left of 0, there is a possibility that x may become a negative integer. No problem. Whatever x is, since x lies to the left of 0, your x may lie here. If x gets further and further away from 0, then it becomes very easy to find that region around x which will have no point of end. But even if your x is somewhat close to 0, you can still find a region around x which has no natural number. So that will show that this x is not an adherent point of n. So except the points of n itself, nothing else is an adherent point of n, and that is why you have this. And a similar argument shows that you have this. Okay, but what about this though? Why is the closure of Q equal to R? Well, the closure of Q is equal to R. So what does that mean? It means that any real number is an adherent point of the set of rational numbers. So you arbitrarily choose any real number. You have to prove that this R is an adherent point of Q. You have to prove that R is an adherent. So in this case, it's not about showing that something is not an adherent point. So it's not about choosing epsilon, but taking any epsilon and then showing that it will work. So you choose epsilon greater than 0. In order to show that R is an adherent point, now you have to prove that this interval, this region around R, having R as its midpoint, has something from Q, because then only it will be an adherent point of Q. In other words, what we are asking is that we should find a rational number Q that lies between R minus epsilon and R plus epsilon. But this comes from a property of rational numbers, namely their denseness, and which is also something we have already seen. It is proposition 5413. It says that between any two real numbers, one of which is strictly greater than the other, there lies a rational number. And that's why every real number is the adherent point of the set of rational numbers. And that is why this is a subset of this closure. But the closure by definition is a subset of R always, and that's how they are equal. And if you are thinking how you have this, then it is mentioned again here. In the previous lemma, the same thing was given in this form. And figuring out how you have this, I am leaving to you. So many things are being left to you so that you also do something. Okay. And this is where I am ending the video. So we will see in the next analysis video what comes next. And tomorrow again we have our usual upload. And tomorrow let's go back to number theory. So with that, I am just signing off for tonight. So see you tomorrow. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.